Okay, so really no one wants to show themselves. That's fine. I can talk to a black screen. Thank you, sir, for your courage. Hi.
Hello. Yeah. So we
Okay.
met last year at ICTP for
Yes, I
youth and high dimension.
recognize you. Of course. How are you?
Good.
Where are you?
Right now I'm in Colombia.
Okay, okay.
Yeah. I used to be in Wisconsin.
Wait, what am I doing? Okay. All right, let's start again. So we discussed the basics of random matrix theory. I've presented the Gaussian orthogonal ensemble, which is the simplest random matrix theory model you can think of. It just represents symmetric Gaussian matrices. And we've seen that despite the simplicity of this model, rich behavior emerge for the eigenvalues, in particular the asymptotic spectrum of the eigenvalues tends to that of the semicircle, which I've shown here, despite the fact that the matrix elements are independent, the eigenvalues are not independent, they are strongly correlated, and their marginal distribution, meaning the probability distribution of one of them, which is really what this law is. This is the, if you want, this law really is the same. This is the marginal law. So this is the integration, or this in the limit. This is the integration of the joint law of eigenvalues with respect to all of them but one. And it has this non-trivial behavior. Okay. Then we presented the V-sharp distribution, which is the next most important random matrix ensemble, which represents random covariances, covariance matrices, so covariances of pure noise. And in this case, the law is that of Marchenko-Pastur, and it is a law which is supported on the positive axis because covariances matrices are, of course, positive semi-definite. Okay. Perfect. And then we have discussed the BBP phenomenology. We have seen that when considering the Spike-Wigner model, meaning a rank 1 perturbation of a GOE matrix, we have an interesting phenomenology that appears, which is that if the signal-to-noise ratio is too small, is less than this BBP threshold, then we only observe the semicircle distribution for the eigenvalues of the data, despite of this rank 1 matrix, which is not coming from the noise, which should participate. It is kind of absorbed by the noise room, and it is hidden by this bulk of eigenvalues, and you cannot say that there was a signal, a rank 1 matrix hidden in the data from the eigenvalues. And actually, you can show, we've seen the phase diagram at the beginning, that you are in the statistically impossible phase. There is no procedure whatsoever that, given the data, will be able to say anything meaningful about the signal. So this is really, this BBP transition is excuse me, no, right now I'm saying something wrong. No, excuse me, there is, depending on the prior, there is potentially this hard phase, which is this region where you can say something potentially about the signal if you have infinite computational power, very large computational power, but efficient algorithms cannot do so.
Yeah, I was gonna say, like, if you have a guess, a really good guess,
Yeah.
with the signal. I mean, I guess
Yeah.
it's exponentially close.
Yeah. So a good guess is a form of a prior. So if you let's say, if instead of saying that your signal can be anything, you can enforce it to belong to a cone, so a region around some guess, of course this picture will change. So this picture depends very much on what is your prior. For a given prior, which in this case is like it's a version of a Rademacher prior where you have just 2 Diracs, the picture looks like this. If instead this one I know it, if instead the signal is Gaussian distributed, which is a very weak prior because it's basically knowing that a vector is Gaussian tells you nothing about its direction because the angle of a Gaussian vector is uniform. The only thing that you know is essentially its norm. In this case, the phase diagram looks like this. The MMSE looks like this, and the lambda IT, the information theoretic threshold, is also the BBP transition. So this is for xi star, which are Gaussian. So in this case, there is only an impossible phase and an easy phase. So in this case, the hard phase disappears, and basically the BBP transition matches the information theoretic transition. Okay, so it means that when you have essentially no prior about the signal, which is essentially the same as saying that it is Gaussian, because a Gaussian prior is only a constraint on the norm, but nothing about the angle, which is really the angle is really the thing you don't know. The norm is a very weak constraint. So essentially having a weak prior about the signal implies that the BBP transition defines also the information theoretic transition. It means that as long as there is no outlier in the data, there is no way to extract the signal non-trivially from the data. However, if your prior is stronger, if your prior, let's say, is let's call this rho tau A plus 1 minus rho tau, sorry, not tau, excuse me, delta in A plus 1 minus rho delta in B. So you have a Dirac in A and B, and you tune this rho correctly, and A and B, you obtain this picture. So you can make a hard phase appear. Okay, so it depends on what's your prior. Okay, perfect. So now the question is, can we derive, what is the key idea to derive such a result? And what I'm going to show you is a very systematic approach which allows to derive spectral densities of many random matrix ensembles. And it consists of 2 main ingredients. The first is that we're not going to compute directly the spectral distribution. We're going to go through another object which is related to it, which is called the Stieltjes transform, which is somehow the moment generating function associated with this distribution. Okay, with this distribution, its limit. So we're going to work with the moment generating function instead of the density itself. And this is a usual trick in probability. It's often easier to obtain equations that characterize the moment generating function than directly probability distribution. And then you reconstruct the probability distributions out of it. So first thing, I'm going to define and work with Stieltjes transform. And the second thing is that I will show you how to obtain an equation describing the Stieltjes transform through a method which is called the cavity method. So, or a leave one out approach. In statistics, they call that the leave one out approach. In physics, you call that the cavity method, and I will tell you why it's called like this. Okay, so let's define. Again, you don't have to read everything and just focus on what I'm showing. We need to define the so-called Stieltjes transform, and which is related to also the resolvent matrix. So what is the resolvent associated with the matrix? It's another matrix which has the same dimension. And so if I give you an n by n matrix H, which may come from the GOE ensemble or from any other ensemble, I define its associated resolvent, denoted capital G, that depends on an argument Z, which is a complex number, and it is equal to Z times the identity minus H inverse, and this inverse is in the sense of matrices, okay? And this Z can be any complex number apart from the eigenvalues of the matrix H. And indeed, you see that if I plug here an eigenvalue of this matrix, this object is not well defined. It will explode. Okay, there will be a pole. So here I'm removing the possible poles, but apart from that, Z can take any value. So this is a complex valued matrix related to the inverse of the original matrix. Okay. What I'm going to show you is that somehow this resolvent matrix is easier to work with than the matrix you want to study directly. And secondly, it contains somehow the same information. Okay, you can extract the spectral density of H and properties about its eigenvectors and all that directly from the resolvent. Notice actually that this resolvent matrix, which by the way we call resolvent because it allows precisely you to resolve many problems using it, the resolvent has the same eigenvectors as H, right? Because if I add a matrix proportional to the identity to a matrix, I'm not changing the eigenvectors. So this Z identity minus H is just a constant shift by minus Z of all the eigenvalues of H. And then I'm applying the inverse, and the inverse operation is like doing the inverse of the eigenvalues, but the eigenvectors are untouched. Okay? So if I do the spectral decomposition of H as sum of lambda I, VI transpose, where VI's are the eigenvectors of H, then GH of Z is sum of VI transpose, same eigenvectors, but the eigenvalues have been shifted. Okay? This is this matrix. Perfect. So now that we have this matrix, I can define the resolvent. The resolvent is simply the trace of this matrix the Stieltjes transform is the trace of the resolvent divided by n, so that this has a limit when n goes to infinity. This remains of order 1 when n goes to infinity. You can think of this 1 over n times trace as like an empirical average. I'm averaging over the diagonal, or equivalently over the eigenvalues. Of course, the trace is the sum of the diagonal elements, but it's also the sum of eigenvalues. So I'm doing an empirical average of the eigenvalues of this matrix, and I take an expectation over the law of this matrix, which could be a GOE matrix, and I take the limit. Okay? And this can be written equivalently. So I ask you to check this equality, but this should be direct. This can be written equivalently as an integral over the spectral density, the asymptotic spectral density of the matrix H of Z minus lambda. Okay? So this, check it, but it should be direct. Okay? So you see, again, this is an empirical average over the eigenvalues, and this is indeed, this operation is an average over the spectrum, and the function that I'm averaging, the eigenvalues of the resolvent are indeed 1 over Z minus lambda I. So here I'm doing the average of z minus lambda with respect to the empirical spectrum. So these two quantities are indeed the same. Okay. So this is a definition. This is the Stieltjes transform. Stieltjes was a mathematician. Perfect. So why is this a nice object? Because we will see that it's easier to derive an equation for the Stieltjes transform rather than for the spectral density directly. And the second thing is that they're one-to-one connected. Okay, if you know one, you know the other, and vice versa. In particular, the Stieltjes transform is the moment generating function associated with the spectral density. So what does it mean? It means that if I take the derivative of the Stieltjes transform with respect to 1 over z, the k plus 1 derivative with respect to 1 over z, and I look at this derivative around z going to infinity along the real axis, because z a priori can be any complex number, then I obtain k plus 1 factorial times the kth moment of this probability distribution, right? This is the definition of the kth moment. This is mk, right? It's the expectation with respect to the spectral distribution of lambda to the k. So it's the kth moment. And of course, if you know all the moments of a probability distribution, you know the probability distribution itself. You can characterize equivalently a probability density in terms of its expression or of its moments. Okay, and there is a one-to-one correspondence between moments and probability distribution. So this formula tells you that somehow, even if this is through this implicit relation, in the sense that, I mean, this tells you that the Stieltjes transform contains the information about all the moments of the spectral density and therefore contains the spectral density itself. You should be able to rederive it from the Stieltjes transform. Of course, in practice, imagine that you know this Stieltjes transform. There is some God that gives you a formula for it. You will not compute one by one all these derivatives in order to try to reconstruct the moments. And then, by the way, it's a non-trivial problem to reconstruct the probability distribution given the moments. Okay, this is a well-defined mathematical problem, but it's not an easy one. In theory, you should be able to, but it's not so easy. So this formula is telling you that both objects, the Stieltjes transform and the spectral distribution, are somehow equivalent, contain the same information, but this formula is not so useful. You cannot use it concretely to reconstruct rho from J. Okay, so we need something else, and this something else is called the Stieltjes inversion formula. Okay, so this is the key connection between the two, and the reason why, once we know G, we can get H in a concrete and useful manner. Okay, so let's see what this formula is telling us. This formula is telling us that if you know the Stieltjes transform associated with the spectrum of a random matrix, when this random matrix has been taken to be very large. So really, this notation you see with an H which is not bold, like for the spectral densities, emphasizing that this H is not anymore a fixed matrix. We have taken the system very large, so this G only depends on the distribution of the eigenvalues, okay, of the associated random variable, which is this infinitely large matrix. Okay. Okay, so this formula is telling us that if we know the Stieltjes transform, let's evaluate it in lambda minus a small imaginary part. Epsilon is positive, is a small positive real number. So I remove a small imaginary part to lambda. I take the imaginary part of this complex valued function. I divide by pi, and I take this imaginary part going to 0. Or it goes to 0 plus with a minus. So this goes to minus 0. It's an imaginary part coming from below, going to 0 from below. And this gives the spectral density. So this looks a bit, looks like a weird formula. Where does it come from? It's not so evident why this would be true, but actually the proof is very simple. So why not doing it? Okay. Before proving this, yes.
I was going to add, it looks very similar to the, so if G is the polarizability of like a molecule, then rho is the cross section. And actually we have the exact same formula.
Okay.
It's 1 over pi, the imaginary part of the polarizability, slightly shifted.
So I guess that there must be a fundamental link with the RMT, yeah.
Yeah, it seems interesting because the G is like a green function. That's what I'm kind of conceptualizing.
Yeah. True. And actually, even in random matrices, sometimes people call the resolvent or the Stieltjes transform the green function. Yes.
Oh.
Yeah, it is connected. Yeah. Thank you for the remark. So, yes, please go ahead. There was a question. I've heard someone.
Is there any question?
Okay, I guess. All right, so let me prove this formula. It's very simple, so it's worth doing it. So the way we're going to prove it is just verify that it's true. So we're going to start from the right-hand side and verify that this identity recovers the spectral density. Okay? So let's do this. So if you write down the Stieltjes transform of lambda minus epsilon and take the imaginary part, it gives this, simply by definition. I'm taking the imaginary part of the definition of the Stieltjes transform evaluated in lambda minus I epsilon, and this average there is part of the definition, right? Because the J of lambda okay, so I'm using just the definition. And this equality is just by multiplying the numerator and the denominator by the complex conjugate of the denominator. The denominator is a complex number, so I don't like to have a complex number at the denominator, so I multiply the top and below by the complex conjugate. So what appears at the bottom is the norm of this, is the modulus of this complex number, and the imaginary part of the complex conjugate of this is indeed just epsilon, right? So I have my epsilon that appears here. Perfect. And what you recognize here now inside the integral is called the kernel. It's this kernel. So sorry, someone has the microphone on and it's a bit disturbing. Okay, thank you. So we have this kernel that appears here, which is called the Poisson kernel. It's just a function. And the thing is that this object, this integrand there, tends to a delta function when epsilon goes to 0. Okay? So this you can verify. Let's try. Sorry.
Please switch off your mic, everyone. Okay, let me just mute it for all. Huh?
I just did. Thanks. So this object is an approximation of the delta of the Dirac function. Okay, of the Dirac delta function. So you see, indeed, if epsilon goes to 0, assume that lambda is different than mu. then whatever this difference is, at some point epsilon will be much smaller. So this term will win against that one. And so all this will tend to 0. Okay? Instead, if lambda equal mu, this term is not there. And what we obtain is 1 over epsilon, which explodes when epsilon goes to 0. So it's indeed an approximation of the delta function, right? It's an approximation of delta times lambda minus mu. But there is an additional pi, because this delta function is a well-defined probability. It's the integral of it is 1, while the integral of this Poisson kernel is not 1. It's 1 over pi. So you need to normalize it, and this is how this pi appears. Okay? So that's it. So now you take epsilon going to 0. This gives us the pi delta, and the delta function peaks when I integrate the delta function against mu. So essentially this is equal to pi delta lambda minus mu. And so when I integrate against mu, it will enforce mu to be equal to delta. And so I obtain this thing. And that's it. The proof is done. Okay? So very simple, but very useful formula. Okay? Is there a question before I move on to now how to derive the semicircle law for the GOE ensemble using this formula?
Any questions?
Okay, if there's not, that's fine. Okay. So now we know that if we have access to the Stieltjes transform associated with the random matrix ensemble, we have access to the spectral distribution. Okay? So what I claim is that we know the Stieltjes transform for many ensembles. In particular, the one for the semicircle distribution is this one. Okay? So we're going to derive it, if I manage to arrive there. So this is the one for the semicircle, and this is the one for the Marchenko-Pastor distribution. So they're a bit obscure formulas. It doesn't matter. This is just a function that I'm giving to you. It has a certain form. But now I claim that if you use this and you plug it in this formula, there, you will reconstruct the semicircle distribution. Okay? And this is done here. I will not do it. You can try. It's an exercise. You have to be a bit careful, because the square of a complex number here, and then you have a square root. So you have square root of complex number. You have to be a bit careful, in particular for a complex number. Tau, its square root is given by this. So it's you have to be careful with this formula. But once you know this, you just use it in the formula above, in the Stieltjes inversion formula, and you will find the semicircle distribution in just a few lines. The proof is this. Okay? So do it. That's an exercise for you. Okay? Perfect. So this is just a computation. It's not so interesting in itself. It's just manipulating complex numbers below a square root. So it's there is nothing so interesting there. So you can do it by yourself. What is more interesting now? Yes.
A quick question. Yeah. So let's recall. So what's lambda again? So lambda is the.
So lambda. Yes. No. It's not a coupling. Lambda is just an argument. Lambda you mean in what? Where?
Yes, the rho lambda, G lambda.
Lambda, G lambda.
Yeah, in the last expression you just highlighted. So what is that lambda again?
This lambda represents a a possible eigenvalue of the matrix that you're studying.
Yeah.
Lambda
Okay.
lambda means eigenvalue. So this rho of lambda is the probability distribution of eigenvalues of a certain random matrix. Okay? In the limit where this random matrix is very large. Okay, so it's an argument. This is a probability distribution.
Mm-hmm. So what does G of lambda then say? So if I have, I'm trying to think of it in the context, I don't know, maybe this is limiting my intuition, but I'm thinking of it as G lambda like a polarizability.
Like a
G
what?
lambda is universal, like a polarizability. Like, does it mean the semicircle law is always -2 to 2? Like,
The semicircle law is this, yes?
Yes, exactly. It's always -2 to 2. Or that lambda, regardless on the matrix size, it's always going to be
There is no
-2 to
more
2.
matrix size. You see here, I've taken the matrix size going to infinity already.
Exactly. Okay.
Yeah.
Perfect. And so, yeah, lambda is just that x-axis.
It's just the x-axis, exactly. So I'm scanning through all the possible eigenvalues, and this rho is telling me what's the weight, the probability weight, the density of eigenvalues around lambda. Yeah.
Exactly. Okay.
Okay.
Yes.
Perfect. Instead, the G of lambda, this Stieltjes transform, does not have such a simple interpretation. The G of lambda really should be understood as the moment generating function associated with the probability distribution, which is rho of lambda.
Yes.
Okay.
Yeah. So Z doesn't really have a clear.
I mean,
so lambda. Yeah.
Yeah. If you have yeah, I don't know how clear is your intuition about what's the moment generating function. I'm
familiar with moment generating function is. Yeah, I'm in the context of like it's the Fourier components for that, but then there's the Stieltjes transform, which I guess is similar to like a Fourier transform, but it's different. And so Z is that transform variable.
Yeah. I mean, it's a Fourier transform in the sense that it's a change of it's a bit like a Fourier transform. You're going from the space of eigenvalues lambda to the complex plane Z, and working with this function in the complex plane is easier. Like when you go to Fourier space, some things are easier to compute in Fourier space. Then you do your computation in Fourier space, and you go back to real space by inversion. Here's the same. It's easier to compute the Fourier transform if you want the Stieltjes transform. Sorry, and then you go back to real space, to eigenvalue space, by this formula.
And so then, how did you derive G of Z? Because then your derivation then just kind of gave G of Z.
Yeah. It's what I want to do now. I haven't told you how to derive G. So now I want to explain how to derive G. At the moment, I assumed that G could be obtained somehow. Okay? So what I told you is if you can get G through some oracle or some method that I haven't given, you can reconstruct the spectral density. Okay?
Exactly. Okay.
Now I want to explain to you how to get G, which becomes the key question. Okay?
Exactly. That's the question.
Exactly. Thank you. So that's what I'm doing now. So here I haven't done the computation on how to recover the semicircle law given G, but it's just a very simple computation. So this any of you can do it. It's just manipulating complex numbers. Okay. Perfect. So now the question is, the derivation of the Stieltjes transform. So thank you for the introduction. It was exactly this. Okay, and I'm going to do it for the GOE ensemble, but the method that I'm going to show you is much more general. It applies to a very broad ensemble of random matrices that are more complicated than the GOE. You can do that, for example, the next simplest example is the Wishart matrices, and you can derive the Stieltjes transform of the Wishart ensemble by the same method. Okay, but let's do it concretely for the GOE. Perfect. We have 25 minutes. I think it's exactly what we need. So the key method behind this computation is called the cavity method. And cavity method in physics is a generic approach used to derive consistency equations for quantities of interest. So consistency equation means, in general, something of, let's say you want to compute some function, which is what we want. We want to obtain g of z, okay? A consistency equation is something of the form g of z equal to some other function f that depend on g of z. This is a consistency equation. This defines g of z for every z. If you can prove that g of z has to verify such equation where f is known for every z. So for every z you show that this has to be true, then this characterizes j of z. Okay? So this is what I call a self-consistency equation. Okay? It's an implicit solution for a quantity, in this case for a function. Okay, so we want to derive such a consistency equation. And a generic approach to do so is called the cavity method. Okay, so let's see how it works in the context of random matrices. So the starting point to apply the cavity method in random matrices is called the Schur complement formula. And this is a formula that is not just useful for what we're going to do now. I advise all the students to really understand what this formula means and absorb it, because it's extremely important in many, many contexts, in linear algebra in general, and to derive efficient computational approaches to compute inverses, okay, inverses of large matrices. Because of course, as you probably know, computing the inverse of a generic matrix is quite demanding computationally. The complexity, if M is of size n by n, the total number of operations needed to inverse a matrix of size n by n, in general, scales like n cube. Okay? The Schur complement formula is a way to reduce the complexity if you are not interested in getting the inverse of the full matrix, but you are interested somehow in subparts of a matrix, in sub-blocks, okay? So let's see how. Okay, so let's M be a generic invertible matrix, okay, which we divide in 4 blocks, 1, 1, 1, 2, 2, 1, 2, 2, okay? These blocks can be of any size that you want as long as the dimensions match. So this M11 block will be of size little n by little n. Okay. Sorry, I haven't noted. Yes. Excuse. So here in my notation, this matrix is of size t by t. Okay. So the first block there will be of size little n by little n. The block 1, 2 is little n by little n minus t. Then 2, 1 is n minus t times n. And the 2, 2 is n minus t, n minus t. So the matrix looks like this. There is a block there. For example, it could be like this, okay? And this would be n by n, n minus t, n minus t. And we have our two blocks, four blocks, sorry, 1, 1, 1, 2, 2, 1, 2, 2. Okay? Let me just, for convenience, call the inverse of M Q. And I can induce the same decomposition in Q. So I have again my four blocks, which are of the same size as for M. Okay? Perfect. The show complement formula tells us that the inverse, the block 1, 1 of the inverse of Q, okay, is given by the following. So, excuse me, now I think I wrote a typo there. Q, no, this is correct. So, the, no, one second. Inverse of Q block 1, 1 is M1, 1. No, wait, I have a typo. Let me double check. Excuse me. Just give me one second. Yes, no, okay. Excuse me, so here, I will correct in the notes. This is I put the parenthesis at the wrong place. This is Q11, the first block of Q, inverse, and not the first block of the inverse of Q. Okay? So, the formula tells us that the inverse of this block can be related to the blocks of M. And you see, we have M11, M12, M21, and the only inverse that appears is the M22 block. So you see that if you are only interested in obtaining the inverse of a subblock of a matrix, you can avoid inverting the whole matrix. You can instead use this matrix, and the only inverse you will need to compute is the one of that block. Okay? So you see, you want to get information about the inverse of that block, you only need to compute the inverse of that one. So you will gain, because you see, now you need to invert something that can be a much smaller matrix, depending on what little n and t are, but you will gain in computational time. Okay? Perfect. So this looks like a generic linear algebra result. Very nice. So let's see how to use it. Why is that useful for random matrices? Is there a question on this formula, or is the meaning okay? Okay. Yeah, I hope it's fine. So let's see how the cavity method works. Consider H. So now I will index H by its size, because we're going to work with matrices of different size. So just to make that precise, Hn will be a GOE matrix, so symmetric Gaussian matrix of size n by n. Okay. Let me define capital M as Z identity minus Hn. And so what you recognize here is, of course, that M inverse, Mn inverse, is the resolvent. Okay, the inverse of this is by definition the resolvent. Okay, that I will call Gn. Perfect. So if I now do a decomposition of this matrix M in blocks, isolating here on the corner just the first element. So basically, I'm decomposing my matrix M. So it's a square matrix as just first element, first column, first row, and all the rest. Okay? And I'm applying the Schur complement formula on this decomposition. Let's see what happens. If we use the formula, so it tells us that the inverse of the first block of the inverse of the original matrix, so the M, you see, and this is the same as M inverse block 1, 1 inverse. Okay? So if you use this, you realize that on the left hand side, you just get the element 1, 1, the first entry of the resolvent. Because the element 1, 1, this is indeed M inverse element 1, 1 inverse. M inverse is the resolvent by construction. So this is the first block of my resolvent, which is a scalar because I've isolated just one scalar, so it's a matrix 1 by 1. And I take the inverse of this matrix, which is just a scalar, and so it's the usual inverse. So I obtain this. Okay? And on the right hand side, I just apply again my Schur formula. So this is my first block there, my M11, minus my M12, which is there, times my M, the inverse of M22, and the inverse of this block is the resolvent there. That is the resolvent for a GOE matrix of size n-1 now, times my M21, which is there. So this is a direct application of the Schur complement formula. Okay? And why is that useful? Because you see, this looks already very much like a consistency equation. Not really, because on the left hand side, I have something which is related to my resolvent. On the right hand side as well, but it's not exactly the same resolvent. Here, this is the resolvent for the system of size n, or a matrix, a GOE matrix of size n, while this is the resolvent for a GOE matrix of size n-1, right? Because indeed, this matrix, by the way, is just a GOE of matrix of size n-1, right? If you take a GOE matrix and you just take a subblock, you take a GOE matrix here, the subblock there is itself a GOE matrix with the same statistics, but just of size n-1, okay, by definition of what a GOE matrix is. So I have an equality that relates the resolvent for the system of size n and the one for the system of size n-1. So it's not yet a consistent equation because I don't have the same on the left and on the right. But now I'm going to use the fact that when n becomes large, these two objects, somehow they should be the same. Because when n goes to infinity, whether you look at the matrix of size 10 billion or 10 billion plus 1, it should be the case that somehow their resolvent are essentially the same. And this is the case. Okay? So let's make this argument slightly more precise. I cannot prove every steps, and I will ask you to trust me and to check the references that I'm mentioning there. But I give you the main idea. So let's now, from this equation, derive a self-consistent equation for the Stieltjes transform. So the first thing to notice, so now we are considering that n is going to infinity. it's becoming very large. We're considering a sequence of problems of increasing size and trying to understand what is going on using this equation and simplify it when n goes to infinity. The first thing to notice is that this vector v, what is this vector v? By construction of our, remember, m is z minus a GOE. So basically, we are just shifting the diagonal of a GOE by z, right? So that's why we have this z minus h11 there, because h11 was on the diagonal. But this vector v corresponds to the elements of minus hn, which have been untouched by this z. So they are just Gaussian variables, independent of everything. This is just a Gaussian vector, right? This is what I'm writing there. This v is just a Gaussian vector independent of everything. In particular, it is independent of the elements of this mn minus 1, which is itself a smaller GOE. Okay? And there is an important property to, you can prove it also in one line, you can try. But if you sandwich any matrix, actually, by a Gaussian vector independent of that matrix, you look at the quadratic form V transpose G V, whatever is this matrix there, as long as it is independent of this Gaussian vector, this is approximately equal to the trace of this matrix divided by n, okay? When we take this Gaussian elements in V with a variance 1 over n, this is why the 1 over n appears. Sandwiching a matrix by a Gaussian vector and computing the associated quadratic form, output the trace, okay, by independence of this Gaussian vector from this matrix. So this is an exercise, you can try to show it. So this object, when n goes to infinity, is very large, is very close to the trace of this resolvent divided by n, which is very close, by definition, to the resolvent, to the Stieltjes transform, right? Remember, the Stieltjes transform was defined here. This is the definition of the Stieltjes transform. What I'm claiming is that when n is sufficiently large, instead of having an equality here, you don't take the limit, you have an approximate equality. Okay? And even if you do not take an expectation there, this is still fine, because you have what we call concentration. This object is a random variable, but because it's like an average, it's the average, it's the empirical average of the eigenvalues of this matrix. It's like the law of large numbers. Empirical averages tend to the statistical average, to the expectation when n is large, like the law of large number. So you have a kind of law of large number there, and so whether you consider the expectation here or not, this is not so important when n is large. Okay? So we have this identity. This term here is essentially the Stieltjes transform when n is going to infinity. Okay? Now, let's look at this term there. What can we notice? We can notice that this z is a generic complex number, which is, let's say, order 1. It's independent of n. And instead, this random variable, h11, what is this law? It's the diagonal element of a GOE matrix. So it's a Gaussian variable with variance 2 over n. And when n goes to infinity, this Gaussian variable concentrates onto its mean. So it's very, very close to 0. So we can neglect this quantity because it becomes very small compared to z. Okay? Perfect. And the third ingredient that we need, we have already simplified quite a bit. So with these two equation, we obtain what? We obtain that 1 over G n Z element 1, 1 is equal approximately, and let's say, yes, when n is very large, to Z minus the Stieltjes transform evaluated in Z. So now I claim that also the left-hand side, actually the denominator, is G itself, is the Stieltjes transform itself. We have shown this identity. So in particular, it tells us that the left-hand side is not a random variable. It has to also concentrate. So it means that the diagonal, any diagonal element of the resolvent of a GOE matrix is not a random object. When n grows to infinity, it tends to a constant, which depends on Z, but it tends to a non-random object. This is again concentration. But now I claim that this constant does not depend on which diagonal element you are considering. And this is a consequence of the rotational invariance of the Gaussian orthogonal ensemble. You see, by rotational invariance, the law, what we have said at some point is that a GOE matrix is equal in distribution to any rotation of the same matrix. So this equality in distribution means they have the same probability distribution. And in particular, a special type of orthogonal matrices are the permutation matrices. I can choose a O, which is a permutation, which will change the order of the diagonal elements of my H. Okay? And the law should remain the same. This property extends to the Stieltjes transform, to the resolvent matrix. The resolvent matrix has the same, essentially the same probability as a GOE. The only thing we have done is to shift its eigenvalues by Z, and then we took an inverse. But the law of the eigenvectors is the same. So all that to say that by rotation invariance, if you change two diagonal elements of this resolvent matrix, it has the same law. It means in particular that any diagonal element have the same mean, the same expectation. And because the diagonal elements are equal to their expectation, because we have shown that they are non-random, it means that this G n n I are all equal when n is large for every I. So it means that the diagonal of the resolvent becomes a constant when n is large for the resolvent. And in particular, if they all become equal, they are equal also to the average, the empirical average over diagonal element, which is trace of Gn over n, which is again the Stieltjes transform. Okay, so using all this, what we obtain is that the left-hand side is 1 over the Stieltjes transform, which is equal to Z minus the Stieltjes transform. So we have obtained the self-consistent equation. We have characterized the Stieltjes transform by the cavity method. And so now that you have this equation, you can solve it. And the solution, so it's a quadratic equation. Okay, you can multiply the left and the right-hand side by G. You obtain this quadratic equation. And so you solve it explicitly, it's a quadratic equation, and you obtain the semicircle law. Okay? So why is this called the cavity method? Or leave one out? Because you see the starting point is really that we extracted one diagonal element of this matrix M, and then by the Schur complement formula, we related the inverse of this single diagonal element to the inverse of all the rest here. So we have kind of extracted a cavity in the system. We've done a small hole, which corresponds to extracting this element, and compared that, related that to all the rest of the system. So it's like digging a cavity in the system and seeing how the system reacts, changes. And because the change has to be small, this is what we exploited there. Okay, these are these are consequences of this change being small. You can close an equation on the Stieltjes transform in this case. Okay, so it's exactly 2. So I think this should be the end of the lecture. I know it was a bit dense. I hope you understood at least the main idea. And the main idea is not complicated. It's really just comparing the system of size n with the slightly smaller one, n minus 1. And the relation between the two is this show complement formula, which allows to close an equation on the Stieltjes transform. Is there a question?
Do we have any questions?
What is the benefit of using this approach for I cannot visualize the long-term advantage of this method.
The advantage in what sense?
See, we try to identify a cavity and then try to trace it for the rest of the system. So, why we did it? Like, what is the motivation behind that?
The motivation is because it's the only way to find an equation for the Stieltjes transform. So you see, the Stieltjes transform is related to the trace. It's related to the trace of the inverse of this matrix. Okay.
Mm.
You cannot compute this directly. You need somehow to find an equation that defines it. So basically, you see, what you have somehow is let me try to say it in another way.
So if I'm not wrong, is it some way of like induction method? Like we try to solve it for some part and then.
Yeah, it's similar.
It's exactly like an induction, if you want. So if you want, what you have is this. So you have n inverse, and if I take then 1 over n. So what I want to compute is this, but this is just the definition. So trace of z. And here I'm stuck. I don't know what to do because I cannot compute this explicitly. So this is just the definition, if you wish. Somehow, if I want to make progress, I need to force the same object that I have on the left to also appear from the right. In this way, I will have an equality between something and itself. I will have a relation for the object that I'm interested in. And to find this relation, I can exploit this show complement formula. And from this characterization, from this definition of the Stieltjes transform, I will have the Stieltjes transform that appears again. It's an induction, like you say. And so I can close an equation. It's like this.
Okay.
Okay?
Okay, sir.
Thanks.
Do we have any other questions?
Yeah, I'm just trying to understand why. So the Stieltjes transform, yeah, it's nice. This way of deriving that g of z. However, you can't do this in real space. That is to say, if you have the Hamiltonian matrix, and then you have a submatrix of that and obtain the spectrum, you can't relate it in the real spectrum in some inductive way.
No, you cannot, because you don't. The key point, what allows to get a self-consistent equation is that you have this per block inversion formula. You can relate inverses of smaller blocks to inverse of a bigger matrix. But now if you directly try to relate the original matrix and its spectrum to the spectrum of a matrix from the same ensemble but slightly smaller, you don't have an equation to connect them. You don't have the equivalent.
Yeah,
That's the whole
the
point.
scale matters.
Yes.
Like I said, with very small, like I'm not even thinking about using CJS transform. I'm just saying use the random matrix directly and trying to obtain that spectrum
there
density.
is no obvious way. There is no obvious way how to do it.
Okay. I'm just trying to understand. Yeah.
No, but it would be. It sounds like a more natural approach to try to find directly a self-consistent equation for the spectrum itself. It sounds very reasonable.
Yeah, but there's no. It loses scale invariance though, because then, like I said, when you have very small matrices, then that spectrum is completely unrelated to the infinite.
Exactly. That's exactly the point. But here, because if you want, the fact of working with inverses, the inverse is an operation that mixes all the elements of the matrix in a very non-trivial way.
Exactly. Yeah,
and
exactly.
This mixing induces concentration, even for smaller matrices. So this mixing operation, this inverse operation, is very important to have all the necessary concentrations that allow you to close the argument. While indeed, if you look at small matrices, you don't have concentration of the spectrum and things like this. I mean, I think we're saying the same thing.
Yeah, unless you have thought of like, okay, if you have a small matrix, but it's interacting with the rest of the matrix in some way, maybe there's some hope. Like it's perturbing the spectrum of that small matrix.
Yeah, maybe that's
the cavity way.
Yeah. Maybe it's possible. I don't know. I know that the standard approach is to go through the resolvent. Yeah.
Exactly. Yeah.
Okay. I would like to express my sincere thanks and gratitude to Jen Barbier, to all the participants, to Julio, Arpita especially, for showing their attentive participation, and I thank everyone for their patient hearing.
Thanks a lot. So we'll meet again tomorrow.
Okay, yes.
Thank you, ma'am.
Thank you, Arpita. Thank you, Dr. Julio.
Goodbye.
Thank you. Bye-bye.